Let's start by understanding what work means in a physical sense. Work happens when a force causes an object to move over a distance. In this example, you can see a force pushing a box, which then moves along the floor. The important part is that energy is being transferred through that force to move the object. It's different from just effort or trying hard. Work here specifically refers to the mechanical transfer of energy when displacement occurs because of a force. This straightforward idea is key to many topics we'll explore next. Here, we see how work is calculated when a force is applied at an angle to an object. The key point is that only the component of the force that acts in the same direction as the displacement actually does work on the object. This component is found by multiplying the force by the cosine of the angle between the force and displacement directions. So, the work done is the force multiplied by the displacement and further multiplied by the cosine of that angle. This means if the force is applied directly in the direction of movement, the work done is just force times displacement. If the force is applied at an angle, only part of it contributes to moving the object. This is why the equation has that cosine term to adjust for the angle. Here, we see three different scenarios for work done on an object. When the force and displacement are in the same direction, the angle between them is 0 degrees, which means positive work is done. This transfers energy into the system, causing it to speed up. On the other hand, if the force is applied opposite to the displacement, with an angle of 180 degrees, the work done is negative. This drains energy from the system, slowing it down. Lastly, if the force is perpendicular to the displacement at 90 degrees, no work is done, because there is no energy transfer. In this case, the object maintains a constant speed. Each scenario shows how the direction of force relative to displacement affects the energy within the system. Here, we see how work can be calculated when the force applied is not constant. Instead of a simple multiplication, work is represented as the area under the force versus displacement curve. This means we take the integral of force with respect to displacement. Essentially, by finding the exact area under this curve, we determine the total work done, accounting for any variations in force over the distance moved. This graphical approach provides a precise way to measure work when force changes along the path. Kinetic energy is the energy an object has because it is moving. It depends on two things, the mass of the object and the square of its speed. The formula shows this clearly. Kinetic energy equals half the mass multiplied by the velocity squared. This means if you double the speed of an object, its kinetic energy increases by 4 times, not just 2. So, the faster something moves, the much greater its kinetic energy becomes, which is important in understanding how energy works in moving systems. Now, let's take a closer look at gravitational potential energy. This energy is stored by an object because of its position within a gravitational field, which you can see illustrated here. When you lift an object to a certain height, work is done against gravity, and that work gets stored as potential energy. The equation shows this relationship clearly. The change in potential energy equals mass times gravity times the change in height. So, the higher you raise the object, or the heavier it is, the more energy is stored. This concept helps us understand how energy is conserved and transferred when objects move in relation to the Earth's surface. When a spring is stretched or compressed from its natural length, it stores energy called elastic strain energy. This energy comes from the mechanical deformation of the spring and is represented by the formula U equals 1/2 K times X squared, where K is the spring constant and X is the displacement from the equilibrium position. This stored energy corresponds to the area under the force versus displacement graph described by Hooke's law, which states that force equals K times X. So, the more you stretch or compress the spring, the more energy it stores, and that energy is proportional to the square of the displacement. Now, let's look at the work-energy theorem, which tells us that the work done on an object is equal to the change in its kinetic energy. Imagine a person pushing a block. Initially, the block has a velocity represented by VI and kinetic energy calculated as half the mass times the initial velocity squared. When the person applies a force, the block speeds up, reaching a final velocity VF, which is greater than the initial velocity. Its kinetic energy then increases to half the mass times the final velocity squared. The work done by the applied force is the difference between the final and initial kinetic energy. This relationship helps us understand how forces change the motion of objects by increasing or decreasing their kinetic energy. Let's focus on a practical example involving a car that is braking. We know the car's mass, its initial velocity before braking, and that its final velocity will be 0 once it stops. There's a friction force acting opposite to the car's motion, which slows it down. The goal here is to figure out the exact distance the car will travel before coming to a complete stop. To do this, we'll rely solely on energy principles, specifically how the car's initial kinetic energy is dissipated by the work done against friction. This setup lays the foundation for deriving the stopping distance using these known quantities. Here, we apply the work energy principle to solve for the stopping distance of a car under braking. The net work done equals the change in kinetic energy. Since friction does negative work to stop the car, the work done by friction over the distance d equals the final kinetic energy minus the initial kinetic energy. Because the car comes to rest, the final kinetic energy is 0, so the relationship simplifies, showing that the frictional work equals the negative of the car's initial kinetic energy. Rearranging, we find the stopping distance is the initial kinetic energy divided by the friction force. This tells us that the negative work done by friction perfectly cancels out the car's initial kinetic energy, bringing it to a stop over distance d. Now let's look at the different types of forces that can act on an object. Conservative forces, like gravity and springs, have the property that the net work done on an object moving around a closed path is 0, meaning the energy put into moving the object can be fully recovered. This happens because the work done depends only on the starting and ending points, not the path taken. On the other hand, non-conservative forces such as friction and air resistance cause energy to be lost from the system. The net work done over a closed path is not 0, which means some energy is dissipated, usually as heat, and can't be recovered mechanically. These forces depend on the specific path taken, so the work done changes based on the route an object follows. This distinction is important when analyzing energy changes in physical systems. This slide highlights the law of conservation of energy, which tells us that in an isolated system, the total amount of energy remains constant. Energy isn't created or destroyed. Instead, it changes form. The initial kinetic and potential energy together equal the final kinetic and potential energy. This means that energy can shift, like from motion to stored energy or vice versa, but the total stays the same. Even though mechanical energy might turn into heat or other forms locally, the total energy in the universe is always conserved. This balance is fundamental to understanding how energy works in different systems. Let's look at this pendulum setup where a bob with mass m is held at rest at a certain height h, displaced by an angle theta from the vertical. When released, the bob will swing down due to gravity, and our goal is to find its maximum velocity at the lowest point in its path. This involves understanding how the potential energy from the height converts into kinetic energy as it swings, allowing us to calculate the speed it reaches at the bottom of the arc. Here, we look at the pendulum at the very top of its swing, just as it's released. At this point, the pendulum has no velocity, so its kinetic energy is 0. Instead, all the mechanical energy is stored as gravitational potential energy, due to the height of the pendulum bob above its lowest position. This potential energy depends on the mass of the bob, gravity, and the vertical height it's raised, as shown by the formula. Essentially, this is the total energy available in the system before the pendulum starts to move. Here, we see a simple pendulum swinging, with the mass at the bottom of its path. At this lowest point, the height is 0, meaning there is no potential energy left. Instead, all the energy has transformed into kinetic energy, which is at its maximum. The equation shows that the total energy is equal to 1/2 times the mass times the maximum velocity squared. This is reflected in the bar chart, where kinetic energy is at its peak and potential energy drops to 0. This example demonstrates the clear energy conversion from potential to kinetic energy as the pendulum swings downwards. Here, we see the solution for the pendulum problem using energy conservation. The total energy at the top equals the total energy at the bottom, so the potential energy at the highest point converts completely into kinetic energy at the lowest point. This gives us mgh equals 1/2 mv max squared. When we solve for the maximum velocity, the mass cancels out, leaving v's max equal to the square root of 2 times gravity times height. This means that the maximum speed the pendulum reaches depends only on how high it falls and the acceleration due to gravity, not on its mass. This is an important observation that simplifies understanding pendulum motion. Power is measured as the rate at which work is done or energy is transferred over time. This means it tells us how quickly energy is used or how fast work happens. The formulas show power as the change in work or energy divided by the change in time. The unit for power is the watt, which equals 1 joule per second. So, if 1 joule of energy is transferred in 1 second, the power is 1 watt. This helps us understand not just the amount of work or energy, but the speed at which it occurs. When an object moves at a constant velocity while facing a resistive force like drag, the power needed to keep it moving can be understood by looking at the relationship between force, distance, and time. Power is defined as the work done over a certain time period. Work here is the force applied multiplied by the distance the object moves in that time. Since velocity is the distance traveled divided by the time taken, we can substitute that into our power equation. This simplifies to showing that power is the product of the force applied and the velocity of the object. So, in situations where an object is moving steadily against a resistance, the power required is simply the force pushing forward times how fast the object is moving. Friction causes energy to be lost from the mechanical system, turning some of that mechanical energy into heat. This means the total mechanical energy decreases because some is converted permanently into thermal energy. Here, the equation shows that the work done by non-conservative forces equals the change in kinetic energy plus the change in potential energy. The diagram illustrates this with a block experiencing kinetic friction opposing its motion, and the rough surface beneath it is where the mechanical energy is transformed into heat, represented by the squiggly lines pointing away. This explains why friction reduces the system's usable mechanical energy over time. Efficiency is the ratio of useful energy output to the total energy input, showing how much of the input energy is effectively used for the intended purpose. In this example, out of 100 joules of energy supplied, 75 joules are useful, while 25 joules are wasted. This wasted energy might be lost as heat, sound, or other forms of non-useful energy. Efficiency can also be expressed in terms of power, where useful power output is divided by total power input. Understanding this helps us see how well a system converts the energy we put into it into useful work. This diagram shows how energy flows through a system. The total energy input is divided into 2 parts: useful output and wasted energy. The wasted energy often appears as heat or sound, which means it's not doing any productive work. This happens because no mechanical system can be perfectly efficient. Energy is always lost due to factors like friction and electrical resistance, which are non-conservative forces causing energy to dissipate. Understanding where energy is lost helps us improve and design more efficient systems.